Hey, welcome back. This is Math 0965. We're going to look at complex numbers today. So the one thing that we said about even-powered roots is that you could not figure out like the square root of negative 25. Okay, that would not be real. But today we're going to show you what it is. And okay, so imaginary. First, we need this thing called the imaginary unit. And so what is that? Well, the imaginary unit I is equal to the square root of negative 1. Okay. Other important facts about this thing is when you square it, you just get negative 1. Okay. Okay. So let's play around with this. And so now in this section, we're going to be able to take the square root of negatives. For example, the square root of negative 18. Okay. So what I like to do is kind of march the negative the I part, the imaginary part, out the back, and the perfect squares out the front. So I'll show you what I mean by that. I'm going to factor it. So 18 is 9 times 2. And then I have this negative 1 as well. And then I could use the product rule for square roots or radicals to split this up into the square root of 9 times the square root of 2 times the square root of negative 1. And then we can simplify, right? So the square root of 9 is 3. Then I'll leave the square root 2 there. And then I'm just going to do a substitution for this square root negative 1. We'll say that's just I. Okay. Okay. Usually I will try to put the I sort of at the end. That's pretty much what the book does too, and we'll kind of see why. It's a standard form for a complex number, and we'll always put the I on the right, just like a variable. But sometimes in the book they don't do that, so that's the way I do it all the time. Okay. All right, so, and you should do it the way I do it. Okay. Anyways, the square root of negative 28, what is that? So it's the same game. You're just going to kind of factor it, try to get the perfect squares out front. And then there's this negative 1. And then, either write it out or in your head, you're doing the product rule for square roots. And then the square root of 4 is 2. The square root of 7 stays. And then we have replacing the negative square root negative 1 with I. Okay. Be sure if you're not using the little hooks on your roots that you don't accidentally let the I kind of wander into the root like I'm writing right here on the right. I can't tell if your I is underneath the root or not. That's one of the reasons why I always put the little hook in there to kind of let the reader know. So if you are going to write it without the hook, make sure, and I can't even do it anymore, make sure that you make sure that it's clear that the I is not inside the root. Okay. Okay. Anyways, let's look at another one. Here I have negative square root of negative 108. You throw it out with your calculator. There's a 36 in 108, so it'd be 36 times 3 times negative 1. And again, you're splitting this thing up. 36 square root 3 square root negative 1. So this would be negative 6 square root 3i. Let's look at simplifying this other kind of guy. So this is 20 plus the square root of negative 5. So you'd get 20 plus square root of 5 times negative 1, like that. And it's 20 plus square root of 5 times the square root of negative 1. And then we could substitute in and get 20 plus square root 5i. And then we're kind of stuck. So this brings us to the form of the complex number that we want to write our answers in. And it's always going to be this form a plus b times I. Okay. And we call the a part the real part, and the b part is the imaginary part. Okay. So section 2 here, the complex number. And it has the standard form, which we always want our answers in. and the standard form is this a plus b, and then with an I on the end. That's one reason why I always put the i's at the end, is because we want everything in this standard form. Believe it or not, if you kept taking math, there's actually classes that are completely dedicated to complex numbers. And I've taken some of those classes, so they kind of always want this type of form. So I'm kind of trying to push you in that direction, so you would be consistent with what people do later on. Okay. Okay, so anyways, there's that thing. So at the end of our little exercises, we always want to make sure we're in that form. Okay, long story short. Okay, so let's look at adding and subtracting these things. And basically, you're combining like terms. You're combining the real parts together and the imaginary parts together. Okay, so it just comes down to combining like terms. Okay, so here's 18. They're giving us two complex numbers, 6 plus 5i. And they kind of look like binomials anyways, like 3 plus 2x and that sort of thing. But here they are. The parentheses don't really matter. You need not worry yourself to death over it. All I'm going to do is combine the like terms. So I want the real parts to add those together. Here's the 6 plus the 4. That'll give me 10. And then plus, then you're adding the imaginary parts, right? So the 5 plus 3 is 8, so we'll have 8i, 8 i's, if you wish. Okay, so no big deal there. So addition, pretty simple. Subtraction, of course, there's one extra bit of nonsense that we need to kind of take care of, right? And it's the distribution of the negatives. So if you're subtracting two complex numbers, it'll look like this. To complete the subtraction, though, you need to kind of, distribute this negative. We're kind of used to doing that sort of thing. So anyways, you get 3 plus 2i minus 5 plus 7i. And then we get 3 minus 5 is negative 2. 7 plus 2 is 9. And that would be our final answer. Okay. Let's look at one more. So you can have radicals thrown into these as well. So let's say 2 plus I root 3. And then plus 7 plus 4i root 3. Okay, so here we'll add up the real parts. 7 plus 2 gives me the 9. And then add up the sort of imaginary parts. Say I have 1 I root 3's, and then over here 4 I root 3's. So that's going to give you a grand total of 5 I root 3's. Okay, so 5 I root 3. Of course, I like to write it 5 root 3i to have that form, that basic form that I'm always after. Okay, so a is 9, b is 5 root 3. Okay, multiplying these things works basically the same as distribution and then FOILing. The one kind of factor you have to always kind of remember is that the I squared, I times I, is equal to negative 1. So multiplying, so again, we kind of remind you that I is actually the square root of negative 1, and so when you square I, you just get negative 1. Okay, so I times I is the same as I squared, right? I squared is I times I. Okay, so let's take a look here. And again, we always want our answer in this complex form, the standard form. So let's multiply first. I have 2i, which you think of as 0 plus 2i, times 5 plus 3i. Okay, and so what is this? It just comes down to distribution. So I end up with 10i plus 6i squared. We need to do our, we have to simplify these I squares. I just circled in blue there. So this will become 10i plus 6 times negative 1. Okay, so that will be 10i minus 6. And then we need it in the complex form. So you have to put the real part first and then plus the imaginary part. Okay, let's do 37. So here I have negative 7i times 2 minus 5i. Again, you're just distributing. So you get negative 14i plus 35i squared. simplify the I squared part now. Plus 35, I squared is negative 1. So we get negative 14I minus 35. And then, of course, put it into the standard form. Negative 35 minus 14I. Okay. All right. Multiplying now, where the both numbers have complex and real parts, just comes down to foiling. Both numbers have the imaginary and real parts, excuse me. So I have one complex number, 8 minus 4i, and the other complex number, 3 minus 2i. Okay. So to pull this off, you have to go first, outer, inner, last. Okay, so the first be 24, the outer minus 16i, the inner minus 12i, finally the last plus 8i squared. Okay. Combine like terms and simplify, so I have 24 minus 28i's plus 8 times negative 1. That will be 24 minus 28i minus 8. And then combine your like terms, 24 minus 8, 16, and then minus 28i. Okay. Let's try 45. Actually, let's try 51. No, let's do 45. Sorry for being indecisive there. 3 plus 5i times 3 minus 5i. So we're going to see this later when we get to division. Basically, to perform division with complex numbers, you have to multiply top and bottom by the conjugate. It's just like when you dealt with the rationalizing denominators. Okay, so it's a lot like that. And when you do conjugates in this setting, the imaginary part will go away, and that's what's going to happen here. Okay, they're sort of foreshadowing that process later for later. Okay, so anyways, the first 3 times 3 is 9, the outer minus 15i, the inner plus 15i, and then the last minus 25i squared. Okay, so you see that the two middle guys are additive opposites. They're gone. Then I have 25, and we do our sub for I squared. That's negative 1. So I have 9 plus 25, and we just end up with a real number. So 34. I mean, technically, every real number is also a complex number. So all the real numbers are kind of a subset of the complex numbers. You don't see it, though, because we don't write it, right? So 34 is equivalent to saying 34 plus 0i. Okay, but we don't write that. That's a bit silly. It's silly to have a 0 there, so we just write 34. Okay, but it's there. It's always there in the background, haunting us, so to speak. Anyways, let's have 51, and we have 2 plus 3i squared. So what is that? Well, you got to FOIL it, right? So it's really 2 plus 3i times 2 plus 3i. And then you're going first, 4 outer, plus 6i inner, plus 6i, and then last, plus 9i squared. So I'll have 4 plus 12i plus 9 times negative 1. So that'd be 4. Eventually that'd be a negative 9, so that'd be negative 5 plus 12i. Okay. Okay, great. One small detail that come up in the homework. I'm not going to spend a lot of time on it, but it does come up every once in a while. So this is a warning for you. Make sure you're simplifying the imaginary parts first. So, for example, in problem 55, you have something like negative 7 times negative 2. Okay, I'm going to do it the bad way. So the bad way is to proceed like you did in the previous sections and to multiply negative 7 times negative 2, sort of using the product rule for radicals. So negative times negative is 14, so you get root 14. This turns out not to be the way you do it. Okay, no, don't do it this way. It won't work. The way you want to do it is to first simplify the radicals. Pull those imaginary parts out. Okay. So negative 2 warning. I'll say must pull out imaginary parts first. So you might want to call it, instead of PEMDAS, PEMDAS. Simplify the imaginary parts and then go from there. Okay, so I would rewrite this by kind of shoving the imaginary part out the back door if you need to. This is 7 times -1. This is 2 times -1. And then product rule radical 7 times radical -1 times radical 2 times radical -1. And then do your substitutions. So we got root 7 I times root 2 I. And then we can use commutator properties to rearrange everything. So you get root 7 times root 2, which is root 14. And then you get I times I, which is I squared. And that's equal to root 14 times -1, doing substitution. And so we have negative root 14 as the actual answer, which is what we need to happen. Okay, so just a warning, do the imaginary parts first. Simplify that part before you go and get nuts with everything else. Okay. Finally, then we have division. And to pull off division, you need to multiply by conjugates. So we need the conjugate. And the conjugate is what I was showing you back here. So if you're given 3 plus 5i, the conjugate will be 3 minus 5i. So you just kind of put a negative in between the two if there's not one already there. If there is one there, you just make it positive, right? Okay, so they'll give you some examples of this in the book, like number 50. Here I am, 5 minus I root 3. The conjugate would be 5 plus I root 3. Multiply them out, and the goal is to get rid of the imaginary part. So anyways, 5 times 5 is 25, the first. And then the outer, I have plus 5i root 3, or 5 root 3i if you'd rather, minus 5i root 3, and then minus I squared times the square root of 9. Okay, so this would be 25, and then you see these guys are additive opposites, they're gone. And then you have minus, root 9 times I squared, or I squared times 9. I squared is just -1, so we could replace that, square root of 9. And then I have 25 basically plus root 9, and root 9, of course, is 3. And then 25 plus 3 is 28. So we get rid of the imaginary number. And this process is going to allow us to do division. And when we divide for our final answer, so division, sort of, I guess the reason why we do this is because we want our final answer in that standard form. So your final answer must be in the form A plus BI. And really the only way to pull that off is to do this sort of conjugation process. So let's take a look. 63 is 2 all over 3 plus I. So I'm going to multiply by conjugates on top and bottom. 3 minus I, and 3 minus I. On the top you can distribute. Sometimes it's easier if you just leave it factored, but I'll go ahead and distribute. So I get 6 minus 2i. And the bottom, foiling, 9 first outer minus 3i inner plus 3i, and then last minus I squared. So in the denominator we're getting that nice cancellation. Then 9 minus I squared is -1. 9 minus -1 is the same as 9 plus 1, which of course is 10. And some people want to leave it like that, but again, your final answer needs to be in the form A plus BI, and that's not in this form. So what you need to do is butterfly. So you take 6 over 10, and then minus the 2i over 10, or if you'd rather 2/10 I. Now it's in the form, all you have to do is simplify. So you get 3/5 dividing top and bottom by 2 minus 1/5 I. So it needs that final form, the A plus BI. So A is 3/5, B is -1/5, and then I. Okay, let's look at another one. Here I have 69. So I got 6i all divided by 3 minus 2i. Okay, so I'm going to multiply top and bottom by the conjugate, 3 plus 2i. Okay, so down below I'm getting 9 first outer plus 6i inner minus 6i, and then last minus 4i squared. Up top I'm getting 18i plus 12i squared. Rewriting, simplifying, 18i plus 12 times negative 1 all over, the i's are gone, and then you get 9 minus 4 times negative 1. So let's use commutative property of addition to rewrite the numerator as negative 12 plus 18i. And then that's all over 9 plus 4, negative negative will become plus, that will be 13. And then again, we need the standard form, so you got a butterfly, so you get negative 12 thirteenths plus 18 thirteenths I. Okay, so I need to see that final form. And the next one is the video quiz. I believe there's only 3 questions in this video quiz assignment. This should be the last question in that assignment. So I have 5 minus 2i all over 3 plus 2i. Okay, so to divide these, I need, again, just to multiply by conjugates. So 3 minus 2i. In the numerator, I got a FOIL. So first, 15 outer, negative 10i inner, negative 6i, and last, plus 4i squared. All over first, 9 outer, minus 6i inner, plus 6i, last, minus 4i squared. Okay. So I'm getting 15 minus 16 i's plus 4 times negative 1 all over 9 minus 4 I squared, again negative 1. Okay. 15 plus, that'll become minus 4, so I'll have 11 minus 16i. Downstairs that'll be 9 plus 4, which is 13. And then butterfly, so 11 thirteenths minus 16 thirteenths I. Okay, so that's a video quiz. Number 79 is kind of weird because you're like, what is the conjugate here? If you have, your number is 3i in the denominator, right? So I'm trying to figure out my conjugate. 3i is the same as 0 plus 3i. Okay? So its conjugate is basically 0 minus 3i. In other words, minus 3i is the conjugate. Okay, so you multiply here, top and bottom, by negative 3i. So you get negative 21i in the top, and below we are getting negative 9i squared. So I have negative 21i all over negative 9 times negative 1. So this would be negative 21i all over 9. In other words, dividing 21 by 3 is 7, dividing 9 by 3 is 3, and then I, negative 7/3 I. Or if you'd rather, 0 plus, minus 7/3 I. The real part is just 0. But it is kind of weird to write it like that, so we're just going to write the negative 7/3 I. That's good enough. Okay. Okay, so hopefully that mystery is resolved. Anyways, let's look at the last section here. We have powers of I, and simplifying powers of I. Okay, so the number I is kind of has a pattern to it if you take a look. So this is kind of interesting. I, of course, is just I. Then you get I squared. I squared is I times I, which we know is negative 1, right? And then I cubed is really the same thing as I squared times I. So I squared, I can see from the last one, is negative 1, and then times I, right? So that's just negative I. I to the 4th is just the previous guy, I cubed times I. So I get negative I times I, which would be negative I squared. Then I can replace the I squared with negative 1, and I get 1. and then I to the fifth, and let me write I to the fifth over here to the right. So I to the fifth will equal I to the fourth times I. I to the fourth we just found was 1 times I, and then you get I to the sixth will be I to the fifth times I, which I to the fifth we just found was I, times I squared, times I is I squared, which is -1. Do you see what's happening? So we are just repeating. It's a pattern. Okay, so the cool thing about math, there's all these cool patterns. I to the seventh then is just -I, and then I to the eighth will be 1 again. So you can see I to the first is equal to I to the fifth. I squared is equal to I to the sixth. I cubed is equal to I to the seventh. And then I to the fourth is equal to I to the eighth. And then you could say I to the ninth is equal to I to the fifth. I to the 10th is equal to I to the sixth. I to the 7th is equal to I to the 11th. And I to the 8th is equal to I to the 12th. Okay, so that's pretty cool how it has kind of a circular kind of I don't know. The exercises you'll see in the book want you to reduce higher power. So that's cool. This thing is kind of like another party trick. So I guess this is kind of a different section, but reducing powers of I. Usually what you want to do here is just rewrite things in terms of I squared. So what do we mean? Here's number 85. I have I to the 10th. I'm going to rewrite that using the sort of the power rules. So I could rewrite it as I squared to the fifth, because if you went in the other direction now back to here, you would just multiply the exponents. I to 2 times 5 is 10. So yeah, that's true. And then you could replace I squared -1, and then -1 raised to an even power is positive, -1 raised to an odd power is just negative. So -1 to the fifth would just give you -1. So the key, I guess, to reducing powers of I is to rewrite exponent as I squared, I guess. Okay. Let's try another one. So 89, I have I to the 22nd power. I mean, you could kind of pull this game like we were doing up here, if you could see the pattern, but you kind of have to count up to it, right? So I mean, this would be 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this answer is going to be -1, right? But that takes too much time. So we want a faster way to do it, right? So what we're going to do is just say I squared to the 11th. Of course, I squared is -1 to the 11th, and then -1 to the 11th is -1. So yeah, it's the same answer, but it's just quicker than having to count through, I guess. Let's try another one. 93, I to the 17th. Okay, so this time for the past two problems I had an even exponent. This one's not even, so what you got to do is kind of peel off one of the i's like that. I to the 16th times I, and then you could write that first I as I squared to the 8th times I, and then I squared is -1. -1 to the 8th is +1, and then you just have 1 times I, which is I, of course. And of course you would go back to our chart up here. 17 would be just I. So 97, this one for some reason is a little bit different. You have -I to the 9th. Okay, the first thing I'm going to do is kind of separate off the -1, rewrite it as -1 times I to the 9th. Okay, and then I could kind of distribute the exponent. So you get -1 to the 9th times I to the 9th. -1 to the 9th is just -1. I to the 9th I'm going to rewrite as I to the 8th times I. And then I to the 8th, of course, is I squared to the 4th times I. And then I squared is, of course, negative 1 times I. And then negative 1 to the 4th is positive 1 times I. So you get just negative I. Okay. Okay, so there's a bit weird, but there they are. Okay, so that's the complex numbers and the imaginary numbers. Let me zip into my math lab and see if there's anything crazy you need to worry about. I haven't looked at my math lab yet. I apologize. Let's see, where are you, Pearson? There you are. So as usual, this kind of part at the end here is optional for you to watch. You have to really watch it if you don't want. Assignments. Oh, there aren't many problems in here anyways. Let's take a look. Okay, you can handle that one. You can handle that. You can handle that. You can do that. You can do that. Can't believe there's only like 7 problems in here. This is ridiculous. I must have screwed up something. Hold on. I guess not. Well, there's that. Okay, I'm probably going to have to go back there and change something. Anyways, thanks for watching, and I'll see you next time.